batteries have a positive and negative terminal. And if we connect those, electrons will flow from the negative to the positive side. We call this flow of electrons current. The difference in electrical charge between the sides of the battery is called a potential, which is measured in voltage. This potential is the voltage that batteries are named after. If we have something in between, we can use that flow to do work, like lighting a light bulb or powering your cell phone. This ability to route electricity is what allows us to harness it. But other substances besides wires are able to conduct electricity too. We've all heard that you shouldn't be in or around water in a lightning storm. This is because ionic solutions in water are able to conduct electrons. But what's an ionic solution? Well, water on its own isn't conductive, but water in nature or in your tap is almost never pure because there are small amounts of dissolved minerals and chemicals present. The water in your sink has likely been treated and often contains fluoride ions, which are good for your teeth. For those who have tried well water or spring water that hasn't been treated, there are other ions naturally present in the groundwater, such as calcium carbonate. There are also likely dissolved salts, like sodium chloride, which we know is table salt. Regardless of their source or what they are, many of these compounds will dissolve in water into their ions, which are positively and negatively charged. The water molecules help to stabilize these ions and prevent them from recombining. Instead of electrons moving through solution, we have a layer of ions at each wire that are able to accept or donate an electron. This allows the current to flow. These reactions occur on the wires in the solution, which are collectively called electrodes. The wire connected to the positive terminal of the battery is called the anode, and the wire connected to the negative terminal is called the cathode. The two main reactions that occur are called oxidation and reduction events, or redox reactions for short. Oxidation is the loss of electrons, which occurs at the anode. Reduction is the gain of electrons, and it occurs at the cathode. An easy mnemonic device to remember these is oil rig, which stands for oxidation is loss and reduction is gain. Using electricity to drive these reductions and oxidations is known as electrochemistry. By placing the chemicals of interest into our ionic solution, also called an electrochemical cell, we are able to perform electrochemical reactions. For instance, in the image earlier, we showed sodium receiving an electron and chloride losing an electron. In a real electrochemical cell, sodium wouldn't actually receive that electron. Instead, the electron would be transferred to water. When two electrons are transferred, we would create two negatively charged hydroxide ions and a molecule of hydrogen. On the other side of the electrolytic cell, water would be getting oxidized instead of chloride. This would yield a proton and a hydroxy radical. Once two of these hydroxy radicals are created, they would combine to form hydrogen peroxide, just like the compound you might have in your medicine cabinet at home. This peroxide species would then undergo two more oxidations and give us 4 total protons and a molecule of oxygen. If we look at the combined reactions at both the anode and the cathode, we can see that we've repeated our first hydrogen generating reaction twice. Now let's take this visual demonstration of a redox reaction and turn it into a chemical equation to see why that is. We can individually write the reactions that occurred at our cathode and anode, and when we do that, they're called half reactions. Here we see the reduction half reaction, where we use 2 equivalents of water and 2 electrons to generate 2 hydroxide anions and hydrogen. Below it is the oxidation half reaction, where we also use 2 equivalents of water, but instead we obtained oxygen, 4 protons, and we lost 4 electrons. In order to get our overall reaction, we're going to need to balance our reaction. To do this, we can multiply the entire reduction reaction by 2. That's why our reaction generated 2 equivalents of hydrogen before. Now that our reactions are balanced, we can combine our reduction and oxidation half reactions into one full redox reaction. We can then start to balance our full equation. First, we can remove the 4 electrons on both sides of the equation. We added electrons, we took away electrons. We can then also start to combine the products that formed at the anode and cathode, as they're not separated anymore. When they're mixed, we combine our protons and our hydroxide anions and we form water. And after we subtract the water we made at the end of the reaction, we have our overall redox reaction, which in this case is known as water electrolysis. Electrolysis is a reaction where we cleave molecules with electrical energy. And today, we're going to be trying an electrolysis of our own.